I hope God helps us. So here now we have electric charge, force, and field. In this topic now, what we're going to cover, my advice for you is after covering this thing, these particular things we are covering is what you should get yourself busy with later. Is what you should get yourself busy with later. Don't do some other things. You get it? Just get yourself busy with it and let it be what you'll be treating. Like maybe we're able to take it to page 100. Don't start reading from page 100 again. No, read it from page 1 to that page 100 that we took it to. The course is not so easy to understand by reading once. No, the one you've had an idea about before, then that is what you should concentrate on. I wish you all the best. I wish everyone the best. So let's talk about the first thing we have. That's oh fuck up. I stopped sharing my screen. Okay, so we have force first. I don't want it to be like this. So they said lightning and thunder are two common phenomena in our hot and humid atmosphere in Nigeria. I'm purposely doing it this way because I want us to be noting the words. You know, you have to fill blanks, fill gaps. So to be able to fill those gaps, you'll be like, oh, I've had the word that was inside this place before. I'm very sure after going through it this way and you yourself reading it by yourself, you'll be familiar with the words. Instead of letting us stop at page 150, you now continue reading from 151. You are only doing yourself, please. But 150, start reading from 1 to that 150. Know that this is what I could cover. Then anything coming from those places, you'll be able to answer them. I wish you the best. So lightning and thunder are two common phenomena in our hot and humid atmosphere in Nigeria. Lightning and thunder. So we all know where it comes from. It's due to some chemical activities to actually. So or let me say biochemical activity. So as a physicist, Benjamin Franklin demonstrated as long ago as 1752, that was 18th century, that this at a discharge of electric current in the atmosphere, there is a current that is about 20 kiloamperes. Kiloamperes means 20,000 amperes. 20 kiloamperes means 20,000 ampere. So those are the things I want you to take note of in case they come out of OBJ. So that's why I'm reading them out now. And at that particular point, the temperature is about 15,000 degrees Celsius. The temperature is about 15,000 degrees Celsius. And this lightning developed in a small area, which is about just 20 cm in width. So they said a very important thing about electric charges is that the force between them is very large. That force is what we know as electrostatic force or electric force, the force that exists between charges. When the charges are moving, the force that exists between them is electric force. When the charges are static, that is when they are not moving, when they are at rest, the force that exists between them is electrostatic force. So electric force is when they are moving, electrostatic force is when they are static. So electrostatic is when they are moving, when they are static rather. That they are following a particular path. So that's that as per that. Let's move to the next. Stop there. So they said in ancient Greeks and the likes, what they are trying to explain to us here is that when we have an ebonite rod being rubbed with 4, an ebonite rod being rubbed with 4 is going to acquire a negative charge. So that ebonite rod now is, let's say, put it somewhere. We also have another glass rod being rubbed with silk that acquires a positive charge. When we bring a negative charge and a positive charge together, they attract each other. That is what we call the law of magnetism, the law of electrostatic or static electricity. Because a positive charge is different from a negative charge. So there are different charges. They are unlike charges. They will attract each other. So, and a negative charge with a negative charge are like charges. So those ones will repel each other. So let's say if this is a positive charge, together, a positive charge, together, that's plus another positive charge. Sorry for that, I'm not good at writing stuff like this. So there's going to be a repulsion, let's say R. But if it is a negative charge, a positive charge, together with a negative charge as a minus, they are going to give a force of attraction. So two charges that are like, you can see that plus and plus, they are like. That is a silk rod that is plus another silk rod. They will be repelling each other. They will never want to come in contact. But a positive charge, which is the glass rod now, and the negative charge, let's say the one that the ebonite rod acquires, when you bring them together, they will come and join each other. Why do they join? It is because there is attraction between them. So transfer of electron will occur. So we say that the force exists in between the both of them. Electrostatic force is different from gravitational force. Gravitational force is just ordinary, a gravitational force. But electrostatic force or electric force can be positive or negative. If it is a force of repulsion, then it is negative. It is positive, force of repulsion. So that means the force is what? Positive. F is positive. You are going to have a positive force. But when it is a force of attraction, then F is going to be negative. Those are the few things you should take note of. If you have with your notes, just like jot them down. When you're in the car tomorrow going, just go through the notes. Those are the stuffs you should. That's the way to gather some few things when exam is already at your door. When you're in the car tomorrow going, you can't join. Yeah, sorry. Okay. So that's it. I've actually explained this one now. That's the law. We call it the law of static electricity or the law of electrostatic. That is, like charges like this. Like charges, they repel. That's why I wrote R. And unlike charges, they attract. So why do they attract? Because a force is between them. The force is drawing them together. So that force is called a force of attraction. And the force will have a negative value. So these ones repel because a force that is between them, which is the force of repulsion, is it's not making them to come together. That's why we call that force the force of repulsion positive. So if this was minus and this was minus, so who will tell me the force that will exist between them? If this thing is minus like this, and this one too is minus, force will exist between them. Anybody with the answer?
Yes, it's a repulsive. It's a repulsive force.
Thank you very much.
It's a repulsive force.
Just because they are the same charge. Thank you very much. So that's that as per that. I think we've been able to do. Any question on the law of magnetism like that? Okay, now let's answer this question. It says there are two charged bodies, X and Y, which attract each other. So you can assign, this thing is technical, just try to think about it very well. There are two charged bodies, X and Y, which attract each other. They attract each other. Definitely X can be minus and Y can be plus. So I can say X is minus and I can say Y is plus. Right? So because they attract each other. And I can as well say X is plus, Y is minus. They attract each other. So they are of different charges. So Say X repels third charge body, which is Z. As X is repelling Z, and I said S is negative, please, another person different from the person that just talked now should tell me the charge of Z. What is the charge of the body Z if it repels the body X, which is having a negative charge?
That would be minus.
That
It's
would be
negative
minus.
charge.
With a
Negative
negative
charge.
charge.
It's a negative charge just because it repels another body of negative charge. That's why the repulsion occurs. So now, since it is a negative charge, do you think Z will attract Y or it will
No,
repel it?
it will attract.
It will attract it because we've seen that Z.
Attract.
Thank you very much. So anybody, any question on that thing? Like you haven't understood the analysis now. Let's see. Please raise. You can just talk. I might not be able to discover if you're raising your hand. You can just talk, please. If you didn't understand this thing we just did now. Anybody?
Please,
Like take,
what did you say? You said electrostatic force is addressed, or how did you put it again?
yeah. We have two types of forces of electric forces itself. So we have electric current force. Okay, we have two types of charges according
Yes.
to motion. When the charges are at rest, we call them static charge. Or please mute your mic. Static electric charge. So we call it static electricity. When electricity or electric charge is not moving, we call it static electricity. The room I am in now, there is a circuit here, and there is no charge moving because there is no light. Generator is not turned on. So the electricity is stored into them inside those materials. It's not moving, right? So I call it a static electricity. But once it starts moving, like at the turn on, we've turned on the light. If we've like there's generator or the NEPA brings light, definitely it becomes a current electricity. It becomes a current electricity. Current electricity is the electricity in motion. While static electricity is electricity at rest or electric charge at rest. So the force that exists between two charges at rest is electrostatic force. But when the charge exists between them, that both of them are moving, then it's going to be an electric force. Many people don't differentiate between them, but that's the basic differentiation.
Okay,
So
thank you.
you're welcome, sir. So I think with that, people have been able to get this. Let's proceed. Unit of charge. Charge actually has a lot of units. It has a lot of units. Electric charge has a lot of units. So it has ampere second. It has Faraday as well. It has some few charges as well too. Volt per farad as well too. So, but what I want you to note is that the SI unit is what we'll be working on. So the SI unit of charge is coulombs. Look at the spelling, coulombs. Very important. Look at the spelling. These few things might even come out, and you know 1 mark. You know how important 1 mark is. So coulombs. That is the charge of. That's the unit of electric charge. Electric charge. So it was named after Charles Coulomb, the one that stated the Coulomb's law. So they said they are now giving the definition because the formula for electric charge is originally anywhere, most especially in electrolysis. You'll be getting to use it very well. Just note it very well straight away. If you are with your note, write it down. Electric charge is the amount of current which flows in a conductor in a unit time. So I times T or I dot T. Q equals to IT. That is the formula for electric charge. The for electric charge. So it is derived from the formula of electric current, which is Q over T. So that's why they now give the definition that a coulomb, which is the unit of this Q, a coulomb is the quantity of charge flowing per second, that is the time, through a conductor, which there is a steady current of 1 ampere. I is representing the current. So Miss Joy, please, you'll be helping me a little bit, small. I want you to help me type those things. Send them as in-call message. The unit of electric charge is coulomb, capital letter C, or coulomb. No, pronounce it wrongly because of the spelling. Coulomb, capital letter C. That's the unit of electric charge. So you can as well be writing them down, everyone. The unit of electric current. Electric current is represented as capital letter I, as electric charge is represented as capital letter Q. It might be Q as well. But electric current is represented as capital letter I. These are the basic things I want you to be putting down. So the unit of electric current is ampere. The unit of time is, okay, who will tell me that? The SI unit of time, everyone. Anyone? SI unit of time. Thank you very much. So, thank you. The definition of ampere involves force between current. Yeah, we are going to see this in Biot-Safart's law and in the Ampere's law itself. So the formula I just gave earlier, I didn't know it was written here. Q equals IT. I is the current, T is the time, Q is the electric charge. Okay, conservation of charge. Let me look up the way to explain this one instead of stressing myself through this reading. See, if you have a material that doesn't have any particular room or in a place that there is always an electric appliance there, you can see if electric charge is moving through it, you know that's when there is light, right? You turn it on, it is working. If electric charge is not moving through it, you will know. So what we are saying is that the total charge that was inside that you are using, it might even be the laptop. The charge is moving through its terminal. So the total electric charge in that thing, before you start turning it on, before you start using it, is the same as the electric charge after you turn it on. That is what they are saying. So when you now add them together, because one will be positive, one will be negative, when you now add them together, that's what we call the algebraic sum. It's not ordinary sum. Algebraic sum will now give you, because one will be negative, like negative P plus positive P is going to give you 0. So in the method of charging by friction, that's by rubbing, like the way we charged an ebonite rod by friction, which is discussed in section 3.1. So I've mentioned it now. Charging by rubbing is what? By friction. We call it charging by friction. The algebraic sum of the individual charges, that is, the net charge, always remains constant. Let us before the process of rubbing, that is, I said before transfer of electric charge, the two bodies were electrically neutral. They were having no charge. Having no charge doesn't mean they don't have any charge in them. That means the charge in them counterbalances each other. We have proton in them, we have electron in them. They both counterbalance. No one is deficient, no one is in excess. So that's why we say they're having no charge that is being dominant. Therefore, the total charge is 0. So now, after rubbing one body becomes negatively charged, while another body becomes positively charged. Now, the amount of electric current, electric charge that this one will lose, this is the first body, P. The second body, Q. So P is going to lose 3 electrons. That 3 electrons that is leaving P, where is it going to? It's going to Q. So that means Q will be having 3 electrons, right? Am I making sense? Hello, am I making sense, everyone?
Yes, we have.
I said 3 electrons is leaving P. Since it is only between P and Q, and there is conversation in a closed system, that's a condition they are supposed to put it. In a closed system where energy is not going out or coming in. So the electric current, electric charge that is leaving P is losing 3E, right? 3 electrons. As it is leaving P, Joy, I just got your message now. All right. So I've actually said it too. I've said it too. So as 3 electrons are leaving P, the 3 electrons are entering E. So E is accepting electron, it will become negatively charged. P is giving electron, it will become positively charged. So what they mean by the algebraic sum of the opposite charges, this is 3E. It is equal to 3E. But this one is positive charge, this one is negative charge. That's what they mean by opposite charge. This is what I'm assuring you, that if you could go through this material yourself after this thing, you will understand it very well. So now the algebraic sum means add them together. This is plus 3E. 3E plus This is a negative charge, right? Minus 3e. Now go manage my handwriting. So plus 3e minus 3e, everyone. Anyone to give me the answer? Plus 3e minus 3e.
The answer is 0.
Thank you very much. So that is the law of conservation of charge. That is, in a closed or isolated system, the electric charge before transfer of electron is equal to the electric charge after transfer of electron. When they have not been losing any electron, what was their charge? 0. This is it here. 0, having no charge. So after they transfer electron, we added them together, still 0. So that is what the law, okay, they said the law can be stated as follows. The total electric charge in an isolated system, that is the sum of the algebraic sum of the positive and negative charge present at any time, does not change. That means remains constant. Quantization of charge is telling us that electron is the smallest charge and proton, they have the same charge actually. Just that electron is negatively charged. Please note that very well. I don't know, you might encounter stuff like that. Electron is negatively charged. Electron is minus electron is negatively charged. Electron is negative, while proton is positive. But they both have the same value. So they are the least charge you can see in existence. There is no charge. There are some mysteries of physics. There is no speed that is more than the speed of light. That's 300 million meter per second. 3 times 10 raised to power 8 meter per second. That's a mystery. They haven't discovered that. There is no distance that is less than Planck's length. They call it the Planck's length. Now, there is no charge that is less than the charge of electron. That's what I'm driving at. There is no charge less than the charge of proton, because both of them have the same charge. They have the same magnitude, but different direction. So that is why, and the charge is what? Who will tell me the charge of an electron in case you are not given and you want to calculate? Anyone? It is on my
1.6 times 10 raised to power minus 19.
1.6 times 10 to the power minus 19. What will be the unit? It is a charge.
Coulomb.
Thank you very much. So that's correct.
Newton meter per.
No, it is coulomb. Coulomb. That is the unit of electric charge. Electron is a charge. Proton is a charge. The unit is coulomb. Did you get it, sir?
Okay.
All right. So
yes, I get it.
Okay. Electric charge is negative. Electron is negative. Proton is positive. So that means electron will be minus 1.6 times 10 to the power minus 19 coulomb, while proton will be plus 1.6 times 10 to the power minus 19 coulomb. So what is quantization of charge telling us? Quantization of charge is telling us two things. Number one is that the charge of electron and proton, they have the same charge, that 1.6. It is the smallest charge known. That is the first thing. No charge is smaller than that. The second charge is that, the second thing it is telling us is that anything you are seeing in existence will never have its own charge to be something point the charge of electron. That is, all things in existence have charges that are exactly whole number multiple of the charge of an electron. Look at this, 2e. This is my pen now. If this pen is containing 100 electrons, I will say 100 electrons. It can never contain 100.5 electron. It can never contain 100.7 electron. There is nothing like point. That is quantization of charge. What is the quanta is meaning there? Quantum. It is telling us that it is discrete. Just the opposite of continuous. Okay. So that is quantization of electric charge. And we have the formula here. So if I say, this is the question, a conductor possesses a positive charge of this, how many electrons does it have in essence? They have told you the charge that is there. That is Q. Please calculate it yourself. Q is 3.2 times 10 to the power minus 19 coulomb. That is the charge in that electron. So find N is the number of electron. So find N, how many electron does it have? Find N when the electron is this 1.6. So Q equals to Ne. What is N, everybody? Anybody? What's the value of N?
2.
And
2.
is
Thank you very
Q all over E. Q all over E.
much. Thank you very much. That's good. Q over E. So did you now get the value? The one that said Q over
2.0.
E is 2.0. Very good. So I was trying to wait for you. Very good. Okay. That's been the case now. I think any question on this, anyone? Don't let us waste much time. Any question on this? Page 17. No. We are being slow. Okay. Having said that, look at Coulomb's law. Let me explain the Coulomb's law straight away with this thing. I have two charges in Coulomb's law now. I have two charges. This is a positive charge. This is a negative charge. The Coulomb's law is very simple. In case you didn't know it before, note it very well now. This is the distance between them. R. The positive charge can be positive charge. The first charge is Q1. The second charge is Q2. Definitely, we should be able to say that there is a force between them. If they are both of the same charges, we'll say a force of repulsion. If they are of different charges, we'll say a force of attraction. So let's write it. So now that force depends on two things. What is the two things? Number one, the magnitude of the charges. Number two, the size of the distance between them. Now, Sir Charles Coulomb to us that if they be closer to each other, that is, if Q2 was not here and Q2 was actually here, if Q2 was here and Q1 is still here, so you know they are closer, then the force is going to become more. That means the lower the distance between them, the higher. So if Q1 is more and Q2 is more, the force is going to become more. That is, the higher the masses, the higher the force. Now, as a mathematician, just state that thing. The Coulomb's law thus says that the force that exists between two charges, Q1 and Q2, the electric force that exists between two charges, Q1 and Q2, is directly proportional to the product charge, the square of the distance between them. That is Coulomb's law. There is no way you won't encounter such thing in the exam. They might not ask you to state it. They might state it and say, what is whose law? You just say Coulomb's law. Very well. Let's see. Okay, he said he observed that the electrostatic force between the two spheres is proportional to the product of the charges and inversely proportional to the square of the distance apart, the distance between them. So that is what we call Coulomb's law. So having this now, this is the sign of proportionality. This thing you're seeing here is the sign of proportionality. We have to change it to an equation. To change it to an equation, we introduce a constant. For those of us that know variations, so this is not ordinary variation. We have types. This is what we call joint variation. It has inverse variation in itself, and it has direct variation as well. We call it joint variation. So F equals K Q1 Q2 over R squared. They are supposed to put K here. Here. So no, disturb me. Excuse me, please, everyone. Let me take care of this, please.
So basically, there are people that manage establish
Please, so can I get this lecture now on video record later?
Yes,
I
you
think
can.
somebody is doing it.
Yes, you can.
Can I get it later because I need to attend to something that is very urgent?
Yes, you can. Teammate, you are there, right? Someone is
Prodigy, can I
recording.
get it? Okay.
You
Okay,
get
Prodigy, I'll
it.
get it from you. I'll get it from you later.
You're welcome.
Thank you very much. Thank you. Yeah.
Okay. Sorry for that. I had to move out of the place I was in. So now, are we together now? Can you all hear me?
Yes.
Yes, we can.
Thank you very much. Okay. So we said this thing now, they're supposed to put F equals KQ1 Q2 over R squared. The K will be the constant. But in physics, we don't just assign constants anyhow. The constants have their own foundations. Where do they come from? So the constant in Coulomb's law comes from this thing. We call it the Coulomb's constant. This K, we call it the Coulomb's constant. So how do they get the Coulomb's constant? It is 1 over 4 pi epsilon. It is called epsilon. So this epsilon or epsilon naught, I write it as epsilon naught. That's what everyone writes it as. I think this is just some typo errors. So 1 over 4 pi epsilon. Epsilon naught is known as the free space permittivity. So if it is in a vacuum, it will be permittivity of free space. If it is not in a vacuum is free space, something that does not contain anything. A vacuum is free space. That's another thing. Does not contain anything. A vacuum does not have any matter inside it. No matter at all. No air, no light, nothing, nothing. That is what we call a vacuum. So free space permittivity is epsilon naught. But this one now, epsilon, is saying ordinary, it depends on the material, the medium, the material that surrounds it. If it is not free space, if it is in the air, so it will be the permittivity of air. Permittivity of air is 1.0005 times the permittivity of free space. They are approximately the same thing. So they said we shall see later. So now this thing now for air, it has its own value. K for air is a constant. You know the constant will always have value. The value of K for air, please someone should tell us so everyone will write it down. I don't want to be writing with this drawing stuff. I'm not so comfortable writing with it. So anyone with the value of K, you might not be given an exam. The value
9
of K,
times 10 raised to the power 9.
9 times 10
Newton.
to the power 9. So the unit is
Yeah.
as thus. Everyone, Newton meter squared,
A
Newton
column square.
meter squared per coulomb
A column square.
squared. That's it. So this is the unit of free space, and this is the unit of permittivity. Permittivity. It has an opposite. We call it the permeability. We might get there hopefully. So this is permittivity. So the thing is now they wrote it here. So this is the value of permittivity itself. So 9 times this is the value of K. K is 9 times that thing that Ms. Joy just mentioned for us is the value of K. So F equals this now times Q1 Q2 over R squared. We've done many things that involve these things before. Don't let us waste much time on it. So this is a question. It says a charge coulomb.
Yeah, I think the network is misbehaving.
Please, sorry, that question he was about to ask us there in that our course material. Let's try and solve it. I think the answer there is wrong.
Which question is that?
We did not even see the question.
Are you with your course materials? Because it's there. The question is there. Let me read it out. A charge Q1 equals to 5.0 microcoulombs is placed 30 cm to the west of another charge. See, Muna just check page 18, I beg.
You know what? Just copy and paste the question on this message chat.
Okay.
I think that the way they would solve it is correct. So I believe that the answer also will be correct.
I would suggest at least the person with the question should kindly share his screen at least. It will enable other people to get the correct question.
They changed the centimeters, the distance from centimeters to meters square, so that it will coincide with the value of m, which is a Newton meters per second square. So they changed the value of the distance r. That's what happened there. That is why you thought maybe it was not correct, but it's correct. Look at it. It's 30 centimeters. So they changed 30 centimeters to meter square. That's how they got 0.30 meter square.
We're not seeing anything.
Sir, can you kindly share your screen for us to see what is going on? You're telling us to see, but we're not actually seeing anything. Can you
The question is in the comments,
okay,
in the chat section.
Let him come and rectify it, sir.
Okay, what was the issue? Have you also solved the question?
Not
Anyone
at all.
with the answer?
Sorry, Ali. The question here, the answer gave us the answer inside the course material gave us -6 Newton. Yeah. Meanwhile, I'm getting 5 point.
5 points, okay.
5.994 Newton. No minus sign. That's like
look at it. Listen, the thing is lying on them in the material. The question we are asked to solve here is 5 coulombs and 12 coulombs. We know that this is a force of repulsion. The force of repulsion will be positive. But when they are solving it, look at my screen. They started using 5 coulomb and -12 coulomb. That is why they had a negative answer in the material. So don't worry, don't be confused. Don't worry. They used F equals 1/4 pi epsilon naught Q1 Q2 over R squared. What is 1/4 pi epsilon naught? That is 9 times 10 raised to the power 9. Times Q1 is 5 times 10 raised to the power -6 because it is a microcoulomb. Times Q2, they gave their own Q2. They are using -12. So definitely their question, maybe there is a typo error in their question. Maybe they wanted to write -12 microcoulomb. So did you get where the issue is now? Hello?
yes, thank you.
Is it clear? All right. So please, for those
not clear? It's not clear from my end. At least maybe you can come again. It's not clear from my end.
Okay.
Yeah, please.
So what I'm saying is that it's the question that is causing confusion. What you are given to solve, you solve it correctly. What they gave here is not what they solved. That's just it. It's a simple mistake or a simple change, rather. Q2, they wrote Q2 equals to -12 microcoulomb, right? And here they said the question I asked you to do is 12 microcoulomb. And now they are solving -12 microcoulomb. And that's not going to affect your answer. It's only going to give it negative sign. Finish. So they said the minus sign shows that the force is in the negative x direction. That is towards what? Therefore, it is a force of attraction. The force is a force of attraction. You might not even need to solve before you know it is a force of attraction. Q1 is positive, Q2 is positive. That's a force of repulsion. But here, Q1 is positive, Q2 is negative. That is a force of attraction. So that's how it is. You treated stuff like this several times. Okay? System don't load now. So principle of superposition. Principle of superposition states one thing. I won't be stressing myself on it at all because there is no way you will encounter a question that you'll be asked to state principle of you'll be asked to work with principle of superposition. There is no way. I assure you that. The workings are always very long. So, but one thing I want you to note is that principle of superposition explains how we can add vectors, how we can add forces vectorially, how we can add magnitudes vectorially. Sorry. How we can add electric forces, how we can add them vectorially. I've explained this thing very well. I took my time to go and check that if you don't know some basic. I don't want to start explaining all those basic stuffs here again. It will be useless. Yes, because there is no way you will go and do that in exam. Number one. Number two is that it's going to chop our time. We are still in page 19. So look at where the principle of superposition is working. They said this is a force Q1. This is another force Q2. This is another force Q3. Force Q1 and force Q2. There is a force charge Q1, Q2, Q3. Charge Q1 and Q2. There is a force existing between them. Force F12, F12. That force is mean. That force is a force of attraction. Force of attraction, that is -1 coulomb and 2 coulombs. So the force that exists between them is the force of attraction. And Q1 to Q3, the force that exists between that one as well is a force of attraction. So we can see that two different forces are having effect on Q1 alone. We have F12 is having effect on it, F13 is having effect on it. So to get the total forces of Q1, we must use the superposition principle. That is, use the Coulomb's law to find the F12 force. Q1, that's F12 is equals to 1 over 4 pi epsilon naught Q1 Q2 divided by 10 squared, right? So find F13, that is F13 equals to Q1 Q3 divided by 0.2 squared by converting it to meters. So after getting your F1 and F2, the principle of superposition is now that you say the total F is equal to, the total F squared. Okay, you all know Pythagoras theorem. F12 squared, F13 squared, F1 squared. This is the hypotenuse. This is the, I can call it the opposite. I can call it the adjacent since I don't have an angle here. So F squared, Pythagorean theorem says in a right angle triangle, the square of the longest side is equal, that is F1 squared, that's the longest side. This is the principle of superposition now. The square of the longest side, which is F1 squared. So is equal to.
Please, I would like to suggest something. The course material, the questions here are very confusing. Can we just solve something out of the course material, please?
What's that? So F1 squared, that is the hypotenuse, squared, is equal to F12 squared, that's F12 squared. This is the principle of superposition, F12 squared plus F13 squared. So that's the total force acting on this thing. Normally, you would have added F1 to F13 to know the total force. Like just add them together easily. But what the principle of superposition is telling you is that you can't just add them like that. This is a vector. Vectors cannot be added as scalars. Vectors are added in either analytical method or geometrical method. So this is the geometrical method of adding vectors. We call it the principle of superposition. What they are using here is known as the triangle method of adding vectors. So if okay, let me talk to my guys first. So now this is it, and with that they got the value of, to get our f now, our f1 is going to be the square root of f12 squared plus f13 squared, and that's what they are doing here. That's what they are doing here. So they are finding the direction as well using tan theta equals this. So it's because you might not solve stuff like that in exam. That's why I don't want to stress myself. An electric field is a force. See, they said just as a football field in an area where the game is played. If a very small positive point charge Q, if a very small charge Q is placed at any point in an electric field and it experiences a force, that is, it feels that a force in it or a force is repelling it, definitely the field strength, if a positive charge or negative charge is placed in an electric field and it experiences a force, that force that acts on it, that force that it experiences in that region at that point, we call it the electric field. So we say electric field is the force per unit charge. It is F over Q. Electric field, this is a mistake. They are supposed to write capital letter E. Electric field, this is, they are writing epsilon. They are supposed to write capital letter E. So electric field is equal to force over charge, F over Q. Are we moving together, everyone? Hello?
Yeah.
If you don't get, let's just know. So E is an electric field. So the electric field is always a vector quantity. That is another thing. The electric field is a vector quantity. So calculation in electric field. The formula for electric field, I would have loved to derive it again, but maybe you can go and look at the past videos. That's what they're explaining throughout here. Electric field is what? Force per unit charge. That is F over Q. That is the formula. Electric field is F over Q, capital letter F over Q. So what is now F? Coulomb's force. You know Coulomb's force is this, right? So taking the Coulomb's force dividing by Q, you are going to have 1 over 4 pi epsilon naught Q over R squared. So this is the formula for electric field. Why are they writing like this in this material? E equals, that's electric field, equals K. K is what? 1 over 4 pi epsilon naught. We all know that. K divided by R squared times Q. So KQ divided by R squared. So KQ divided by R squared. K is 1 over 4 pi epsilon naught. So KQ divided by R squared. This is equal to, is not there. So that is the formula for electric field. E equals 1 over 4 pi epsilon naught Q over R squared. That is the formula for electric field. We also call it electric field intensity. It is the force per unit charge. You might not be, I don't think there will be any cost to calculate anything involving it. Moreover, if I were to have explained this in one class like that. So I won't be explaining this again. There is no way you'll be asked to solve stuff like this in the exam, or there is no way. So, yeah, battery is very low. Subhanallah. So I've logged them with another stuff. My system went up, seriously. My system went up. So can you all hear me?
Yes.
Yes, we can hear you.
Yes.
Yes, we can hear you.
So let me quickly try to share the stuff here. So that's electric field. We said electric field is the force per unit charge. The formula is F over Q, capital letter F over Q. So where Q is the electric charge, capital letter F over Q. So from deriving it from formula, we discover that E, that's the electric field, is equal to 1 over 4 pi epsilon naught times Q divided by R squared. Can showing now? Is this one showing, please?
Yes.
Yes, it's showing.
Yeah.
So an electric field is a region where an electric charge experiences a force. So calculation involved in electric field is passed through also. So when we talk about the field lines, electric field line, what does it imply? Electric field line can be represented by electric field can be represented by electric field lines or lines of force. We call it a line of force. So that the field line is at the point is all these are useless for now. What I'm going to tell you is that the electric line of force are imaginary lines. We call them electric line of force or field line. They are imaginary lines that shows the direction that a positive charge will pass if it is placed in an electric field. Look at this direction now. If a positive charge is placed at A, this is the direction it will pass through, this indication of the arrow. If it is placed at B, this is the direction. You can see it is tangential to the point. So if it is placed, it is going to show the direction which a positive charge will pass through when placed in an electric field. That is what we call line of force. So now, from that one now, we can tell ourselves what we mean by position charge. We'll say position charge, a point charge. A point charge is also known as a position charge, like charge of an electrode or charge of a proton. A proton is positively charged. The electric field will be going outward. So that outward, we call it radially outward. Radially outward, just like what we have here. This is for positive charge, pointing out. That is, it is pointing out. Electron will be going out. Electric charge, that's the line of force. It is pointing outward. I think I'm going to use the board eventually. So if it was a negative charge, the arrow will be facing inside. It won't be facing outside. The arrow will be facing inside. It won't be facing outside. So that's what we have here. That's what we have here. They didn't do it well. Let's say this is a positive charge. This is a negative charge. They will attract each other. That's why they are forming something like a bulb, like onion bulb. You can see electron is, they do it roughly. Electron is moving from the positive charge to the negative charge. So they are going to meet. But when they repel each other, look at what we have here and the one under this one. They are not meeting each other. Instead, this one is it is going to the top, this one is going to the down, this one is going to the down, going to the top. Instead of meeting each other, they are not meeting each other. So that thing explains that law again, that the nature of field lines, two unlike charges and two like charges. Unlike charges will come and meet together and form an onion like this, onion bulb. And like charges will be separating from each other. I've explained this thing very well in one of the classes. So don't let us waste much time on things we passed through before. Look at the summary. There are only two types of electric charges, and they are called positive and negative. The law of static electricity says like charges repels, while unlike charges attract. The unit of electric charge is coulomb, C, and charge is always conserved. That is the law of the conservation of electric charge. That is, the algebraic sum of charges in a closed system is constant. It does not change. Electric charge is quantized, occurring only in discrete amount, not in continuous amount. Not continuous as in 1.1, 1.2, 1.3. No, but discrete 1, 2, 3, 4. That is That's about quantization. And the force between two charges is proportional to the product of their charges and inversely proportional to the square of the distance between them. Who can tell us that statement? What is it called? What is the statement called? The statement we just stated now. Hello?
Coulomb's law.
Coulomb's law. So, and the value of, they are giving us the formula that F equals 1 over 4 pi epsilon naught Q1 Q2 over R squared. So the value of all this now, all these things, 1 over 4 pi epsilon naught, all this 1 over 4 pi epsilon naught, the value altogether is 9 times 10 raised to power 9 Newton meter squared per coulomb squared. So they said electric field at a point in space is defined as the electric force exerted on a test charge or a point charge placed at that point. So electric field E is equal to F, this is supposed to be F over Q. Electric field E is equal to F over Q. That is that. So from that, we were able to deduce this formula that E equals 1 over 4 pi epsilon naught Q over R squared. So this R is a unit vector. A unit vector is always 1. So it's like saying we multiply it by 1. This R you are seeing here, it is called unit vector. Multiply that sign on it makes it a unit vector. Multiplied by 1. That's like Q over R squared times 1. That is the meaning. So, okay, they are mentioning it. Where R is a unit vector pointing from the point charge to the location at which the electric field is being calculated. So they said the electric field, due to a distribution of charges according to the superposition principle, is the vector sum of the fields of the individual charges making up the distribution. The vector sum, that's what I said, that you add them, sum, vectorially. You add them vectorially. So that's why they are using the summation form here. Don't let me confuse. Electric line of force are only a visual way. They are mere visual way. It's not like they exist of representing an electric field. The tangent to a line of force at any point shows the direction of the electric field at that point. Like we said at point A and point B just now. This is the line EA. It is tangential to point A. So we say it is electric field at point A. So that's that as per that. Any question on that first unit, anyone? Any question on the unit? Please respond. Any question?
No.
I think someone is raising their hand.
Please speak if you are raising your hand. I'm looking at the screen. I can't still be looking. Don't stress me, Jerry. I can't still be looking at you again. Please speak if you have any question. So Gauss's law, that's the next thing to talk of. We'll talk of Gauss's law. It's a pity I've explained this thing, explain, and we'll still be explaining again. As for Gauss's law, I will implore you to go and watch the video. I'm only going to scale through it right now. So Gauss's law expresses the relationship between an electric charge and electric field. Electric charge is Q, electric field is E. The Gauss's law will tell us the relationship between the both of them. It is also like a law derived from Coulomb's law, or a law that works like Coulomb's law. They said it is a consequence of Coulomb's law. Coulomb's law can be used for anything, just like the Biote-Savart's law. So, but electric Gauss's law can be used only for symmetrical surfaces. The conditions must be symmetrical. Like the Ampere's law, that one too must be symmetrical. So that is the essence of this Gauss's law. Although it contains no additional information, but its mathematical form enables us to solve many problems of electric field calculation far more conveniently than through the use of Coulomb's law. So let's see. Electric flux. Please note this now. I might not be able to read this out. Electric flux is the integral product. So let's just say electric flux is the product of the electric field and the surface area. Electric flux is the dot product or scalar product of electric field and the surface area. That is electric flux. I'm looking for the place they will mention it. This is it. Electric flux is represented as phi, phi. So when we get to a place, the place that we should work more on the board, I will start using the board. I've explained all these things before, so I shouldn't waste time on it again. So phi is equal to ES. E is the electric field. S is the area of that surface. So that is the formula. It is dot product. That is why electric flux is a scalar. Electric field is a vector. The area is a vector. So the dot product of two vectors must give us a scalar. That is why electric flux is a scalar quantity. We mentioned it, that electric field is a vector quantity, electric flux is a scalar quantity. So it's a pity I won't be explaining this here. You might not really need it as well. So let's do something. If you want to, like if you still have the time to go through stuff like this, you can watch the videos for it. So Gauss's law. When we talk of Gauss's law, I'm going to state it straight away now. Don't mind yourself with any fucking stops here. Gauss's law states that the electric flux through any Gaussian surface, the electric flux through a Gaussian surface that is enclosing a charge, the electric flux, that is phi, you can write it down, that phi, the electric flux, phi, through any Gaussian surface that is enclosing a charge Q. Enclosing a charge Q, the electric flux is directly proportional to the charge. That's it.
No,
again, the electric flux, flux through a Gaussian surface. When we say a Gaussian surface, a Gaussian surface is a closed surface, like a cube, a cylinder, a sphere, a cone. It is a Gaussian surface. That's what I mean by a Gaussian surface, a closed surface. So electric flux through a Gaussian surface that is enclosing a charge is directly proportional to the charge enclosed in it. So phi is directly proportional to Q. That is Gauss's law. Q enclosed. Phi is directly proportional to Q enclosed. So the constant of proportionality there is just 1 over epsilon naught. That is the reciprocal of the free space permittivity. So I'm looking for the place. They did not represent that thing like that here. This is just some naughty notes. Oh, I really can't. It's not so convenient to write on this one now. I'm even using phonics. It's not of UPS. Yes. So we know that the S, it depends on the area of that thing. So flux is what? Electric field times area. This is it. Flux is electric field times the area. So cos theta is telling us the cos of the angle between the electric line of force and the electric field. So flux equals to E ds. This is this. Flux this EDS now can be proportional to that charge Q. So EDS is directly proportional to charge Q. That thing is not here. So it is something like this. Instead of this equality sign now, you just put proportionality sign. And this DS now is not having epsilon naught under it. Q enclosed is having the epsilon naught under it. Let's see if you can write it out. So integral of EDS is equal to Q enclosed over epsilon naught. So that is Gauss's law. That's Gauss's law. Maybe later I'll just do one small video to explain that in a bit. So Gauss's law applies to any hypothetical closed surface called a Gaussian surface. We've said what a Gaussian surface is. And enclosing a charged distribution. Those are the two conditions for Gauss's law. Number one, it must be a Gaussian surface. That is a closed surface. Number two, the surface must be having an electric charge enclosed in it. So we have this spherical symmetry. We talked about symmetry. So Gauss's law works with symmetry. We have spherical symmetry, we have line symmetry, and we have surface symmetry. So it's not so useful to be calculating stuff like this now. So because I would prefer we just leave this thing. I've explained them several times before. So I'm just mentioning the important points there now. The long calculations are useless after all. They are useless. All those long calculations. There's no way you do that in exam. So I'm looking for the next thing to talk of. I'll just implore you to know this formula here. This formula here. I'll implore you to know this formula here. This one. So 2 pi RLE equals to Q enclosed over epsilon naught. So, and as for the plane symmetry now, so let me just mention them like that. We have the spherical symmetry. We have what is called the volume charge density. The volume charge density is defined as the charge per unit volume. Finish. Volume charge density is the charge per unit volume. Now we'll say area charge density. That is the charge per unit area or surface charge density. Charge per unit area. And when we talk about the line charge density, we talk of the charge per unit length. Charge per unit length. Finish. For the volume charge density, is going to be Q per unit. That's Q all over volume V, volume of that shape. If it is a sphere, over 3 pi r cube. If it is a cylinder, r squared h. If it is a cube, LBH. If it is a cone, 1 over 3 pi r squared h. Like that. It depends on the material. It depends on the thing itself. So volume charge density, which is represented as volume charge density is represented as rho, RHO. It is a Greek alphabet, rho. So I don't know. I've written rho several times for you guys. I don't know if there is someone that can. Well, just excuse me, please. Let me just use the board. I'll make it snappy. Let's use the board. So you can still continue. Let me get my marker and the stuff to use. So let me just use the board because I can't really explain much that way. So you can continue with 1 or 2 conversations that are beneficial. I'll join in less than 2 minutes. Hello, please mute your mic. Mute your mic. Hello, mute your mic, please. Mute your mic, please. Oh, okay. So now we were talking of the line charge density, the volume charge density. We said the volume charge density is represented as this. This is rho. It is equal to the charge divided by the volume. I'm going to be making it snappy. This is volume charge density. So charge that is in that thing divided by the volume of that thing, that is volume charge density. Area charge density as sigma. So sigma is the charge in that thing divided by the area of the surface. That is area charge density or surface charge density. So that's the formula. And for line charge density, that's lambda. Lambda is equal to the charge divided by the length. So, importantly, what we are trying to draw out is that this times volume gives the charge here. This times area gives the charge here. This times length gives the charge here. So are we making sense with the volume charge density, area charge density, and the line charge density? All right. So that's that as for that. Let's continue with potential, electric potential. When we mention electric potential, we're talking about potential. Potential. What's potential? Potential is a work done. It's a type of energy. So that's why it is measured in joules. So potential is the work done to bring a particular stuff, a quantity. When we say potential, it is just the work done to bring a quantity from where it is until it comes to a point of rest. So if it was in a gravitational field, I would say gravitational potential is the work done to bring a mass to rest. Is the work done to bring a mass to rest. W over m, that is gravitational potential. But now we're talking of electric potential. Electric potential V is the work done to bring a positive charge. Electric potential at a point, let's put it that way. This is a point. Electric potential at a point is the work done to bring a positive charge, a unit positive charge from infinity. Let's call this my infinity. From infinity to that point. What is the work done to bring that charge from this place to this place? That is what we call electric potential. The work done is electric potential. So the formula for electric potential V is equal to work done to bring the charge, work done per charge, W. I don't want to solve much. Remember very well that W is equal to work done, right? The formula for work done is force times distance. So if I said this is the distance from infinity, from infinity, the distance to P is the x. The distance to P is the x. So that will be force times the x. So what is now force in an electric field? Who will remind me the formula for force in an electric field there? Let's see if we are working together. The formula for force in an electric field. Anyone, please just speak out.
Is it Newton? Newton.
The formula. Okay, this is what I'm asking. So this is what I'm looking for. F equals to 1 over 4 pi epsilon.
F is equal to
Q1, Q2 over that's correct. Over R squared. Who's this? R squared. So the R now is what? What is the R I'm talking of? Is the X. So it will be squared. So I don't want us to be doing formulas too much. That's why I didn't want to use 44. So F equals K Q1 Q2 over this K Q1 Q2 over the X squared. So, and what's done is this. So from doing all this together now, we will arrive at a formula for potential. That potential is equal to Q over 4 pi epsilon naught R. Finish. Q over 4 pi epsilon naught R squared. R squared. Okay. R. Ordinary R. So this is the formula for electric potential. This is the basic formula. V equals, you should put it down. V equals minus W over Q. So from derivation, V equals Q over 4 pi epsilon naught. So this is the formula for electric potential. The formula for electric potential. So we have a surface that is known as an equipotential surface. Is there anyone that can explain what it means to us? An equipotential surface.
Remove your hands. Remove your hands.
I should remove, man. What is this? So let's say this is a circle. I have these are the surfaces, right? So let's say this is the surface. Please mute your mic. Please mute your mic. This is the surface like this. So the potential at this point, 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 all at all this point now, having the potential being the same, having the potential being the same, we say they are equipotential. Equipotential. That's the condition for equipotentiality. That's what we mean by that. So work done in an electric field. So work done in an electric field, we remember one formula we just mentioned now, that electric potential is equal to work done over charge. So from this formula as well, you can write your own work done. Work done in an electric field is equal to potential times Q, Abi. That's BQ. So using the mass here now, doing the mathematics here, we're going to have KQ squared over 4 pi epsilon naught R. So this is the formula for work done in an electric field. Work done in an electric field. So there is one important thing. This is a body. This is another point. This is a point A. This is a point B. There is one conservation law that is telling us that if an electric charge is moving from this place to this place, it doesn't depend on the distance, on the path it follows. It doesn't depend on the path it follows. It doesn't depend on the path it follows. The electric potential, if it follows this place, is still the same as the electric potential if it passes straight like this. So that's what we are trying to say at this point. The work done, let's put it that way. The work done, if it passes this place, is the same as the work done if it passes this place. It's the same as the work done if it passes this place as well. So that is what we imply by electric potential and the work done in an electric field. So let's continue. Let's continue. Any question? Any question? Any question, anyone?
No questions.
No.
Let's see. Capacitors. I think that's the next thing. Capacitors. So when we talk of capacitors, what do we mean by that? What do we imply? We're talking about some material that is used for storing electric charge. That is the work of a capacitor. A capacitor is a material used for storing electric charge. So Note very well. If this is a capacitor, if this is a capacitor with a positive plate here, negative plate here, positive plate here, that are separated by distance L, that material will have a particular area, right? So area A. So there is a potential difference at the terminals. When there is, okay, the material in a capacitor, the thing in between these two things is an insulator. It's always an insulator. Insulator. So that insulator is known as dielectric. They call insulators dielectrics. Insulators are dielectric. Who's this person? Please mute your mic. Insulators are dielectrics. So we have different types, right? We have sand cannot be, air, so paper, maker, stuff like that as dielectrics. Any different things, glass, plastic, they can be the dielectrics in between the plate of the capacitor. So a capacitor is used to store electric charge, and the capacitance, which is known as capital letter C, is the voltage is the charge per voltage. That is a particular charge that is being put into this thing, that is being put into the capacitor until a voltage is what? Kindled in it, until a voltage is being disturbed and being brought up in it. When an insulator becomes a conductor, that is what we're trying to say at this point, that still the insulator becomes a what? A conductor. So capacitance is the ratio of the electric charge to the potential difference. That's the electric potential difference. This is the voltage. So the unit of, sorry, I didn't mention that earlier. The unit of potential difference is volt, and it is a scalar quantity. Potential difference is a scalar quantity, and its unit is volt. So capacitor is C, or capacitance is C, and it is equal to Q over P. The unit of capacitance is farad. Farad. The unit of capacitance is farad. You know that the unit of potential is volt, potential difference, and the unit of charge is coulomb. So Q is going to be CV here, right? Who is this person sharing a screen? Is my own showing very well like this? Why I go to my stop where? Yes.
Francis, can you stop sharing?
I can't hear you, Francis.
Maybe he doesn't even know that he's sharing his screen.
Maybe she does.
Sorry about that.
Okay.
Sorry about that.
So C equals Q over B. So I'm thinking of something now. That's the main reason I wanted to use the material. So I won't be going out of what is inside the material. That's the main reason I wanted to use the material. What I'm thinking, I'm not sure if it's. So we have what these things depends on. Firstly, we have types of these capacitance or capacitors. We have several types. So but they are basically divided into two capacitors. We have the fixed capacitor and the variable capacitor. We have the fixed capacitor and we have the variable capacitor. So under these ones now, we have the maker capacitor, we have the electrolytic capacitor, we have the trimmer capacitor, we have the paper capacitor, we have the glass as well, we have more types of capacitors. So they are used and they have their own dielectric materials. So what do we mean by the dielectric? They are the insulators in between the poles of a capacitor. This is the positive terminal of a capacitor
negative terminal separated by to note one thing now. Here, this is permeability, permittivity. If it is having 0 down here, it is epsilon naught or epsilon null. That is permittivity of air. Permittivity of air. That's ordinary for air. And that's going to be 8.5 times 10 raised to the power 12 farad per meter for air. I said air. Free space, sorry, for free space, vacuum. So for air now, it's going to be gotten from one thing. When we say relative permittivity, relative permittivity, the reason I'm doing it this way is I want to draw some vocabularies out for you. So those might be some questions actually. Relative permittivity is also known as the dielectric constant. This is a dielectric now. I'm going to assume my own dielectric is air. I'm going to use that thing to do the workings now. Air. The dielectric I'm using is air, the positive plate, the negative plate, air as my dielectric. So here now I can use epsilon naught, which is that of free space, because this is air. We said it earlier that it depends on the medium. Medium here is not vacuum, it is air. So what do we do? How do we get the permittivity of air? They will give us the dielectric constant. So dielectric constant now is always like this. This is the relationship. Dielectric constant is epsilon R. We call it the relative permittivity of the material, that's of air. The relative permittivity of air, which is also the same as the dielectric constant of air, is this equal to the permittivity of air, the permittivity of air divided by permittivity of free space. Am I making sense? Please, am I making sense? Are we getting the points?
Yes.
Yes.
So, epsilon over epsilon naught. This is the dielectric constant is this, epsilon R. This is the permittivity of that material, air. So I'm talking of air here. If it was paper, it would be the permittivity of paper. If it was mica, permittivity of mica. Ceramic, permittivity of ceramic. That's what we mean. So epsilon naught will be the permittivity of free space. So this is what we call the dielectric constant. That is relative permittivity. So the dielectric constant of air is always equal to 1.005 times the permittivity of free space. So this is the dielectric constant of air is always equal to 1.005. 1.005. So having the dielectric constant of air now, we can have the permittivity of air itself. But those calculations might not be so important. But note very well that this formula is important. Epsilon R equals to epsilon of that material. Any material that is inside that dielectric all over epsilon naught, that is for vacuum. So that is established. So now there is this thing here. Capacitance is equal to, or should I not use capacitance? Let me use epsilon naught straight away. This formula might be useful. It's going to tell you the state of the capacitance and the length. That's why I wrote the length of that. The length means the distance that separates the positive plate and the negative plate. That is L. So, and this is a particular surface, right? So A will be the area of that surface. So this is going to be CA over L. So the formula that we can use to find the capacitance of a capacitor, that we know its dielectric constant. The capacitor that we know its dielectric constant, and we know the length That's the distance between its terminals, and we know its area. We might not even know it. We can just calculate it by ourselves. So the formula is like this. That is C equals epsilon L over A. Right? Very well. Let's try to use this to solve a problem. And you will say we have done capacitance like that. So let's say a capacitance like this now is given. A capacitor rather, like this is given. A square capacitor is given. A square capacitor. A square capacitor is given with a length of 8 centimeter and positive, negative with its. We said dielectrics are insulators. Its dielectric is air. Its dielectric is air. So find the capacitance of the capacitor. If the dielectric constant of air is 1.005, dielectric constant is a dimensionless quantity. It doesn't have unit. Electric constant doesn't have units. So to do this now, we can just use this formula that C equals the permittivity of air the permittivity of anyone with the answer? Nobody is answering.
Please, I'm confused. That's relative permittivity and.
I'm talking to you guys here. Is the permittivity of air given here or not? The permittivity of air, is it given or not?
It's not given. It's not.
You guys
No, it's not given.
Asking since I do get fed up when no one is answering actually. So the relative permittivity is 1.005, and we have this as the permittivity of air. We don't know it. So you just come back here to use this thing. The relative permittivity equals to permittivity of air over permittivity of vacuum. So to get the permittivity of air, you do what? You cross multiply relative permittivity. That's the electric constant times the permittivity of vacuum. Epsilon R times epsilon naught. So C is going to be, E is what? Epsilon R times epsilon naught times this L all over A. A is the area of the thing. This is a square. We said a square capacitor. Formula for area, length times breadth. Since this is 3 cm, it's a square. This one should also be 3 cm. So let's change it to meters. That's going to be 0.3 meters. So the area is 0.3.
You can't see the full board.
The electric constant, that's 1.005 times epsilon naught is that of air, which is 8.85 times 10 raised to power minus 12 times L is the distance that separates them. That is 0.3, right? So 0.3.
Hello, please, we are not seeing the football, please. Please, we are not seeing the football.
All over. A is the area, that is 9 times 10 raised to power minus 2. So doing the mass of our here, we're going to have our value, and anything we get, I'm assuming we have 17 times 10 raised to power minus 5 or minus 10, and that's going to be in, what's the unit of capacitance? Anyone? I've mentioned it here already. The unit of capacitance is what?
Volt.
Farad.
farad. So the unit of capacitance is farad, and that is established here now. So I think that's all about capacitance actually. So we have an RL circuit, a circuit that is containing resistance and RC rather, resistance and only capacitance. So the voltage in that one, let me just give the formula because to derive it, you have to know how to solve differential equation. So let me just give the formula. The formula is given as C R equals to CV naught. CV naught times, open bracket, 1 minus e raised to power minus t all over RC. So this t is known as the time constant. So when the time constant is equal to RC, then we're going to have our R to be equal to CV naught times 0.63 like this. So that's 1 minus e raised to power this. This is if this is equal to this, that would be e raised to power minus 1. So Euler number raised to power minus 1 is always 0.37. So this is CV naught times 0.63. I'm only giving the formula R equals 0.63 CV naught. So this is the formula basically. For when the time constant is equal to RC like this, and the formula becomes this. In an RC circuit, this is important. It is important, note it very well. In an RC circuit, this is in an RC circuit. This is the formula for the resistor. A circuit that contains a resistor and a capacitor. That's what we need. A circuit that contains a resistor and a capacitor. So that's that as per that. I think any question on that capacitor, please. If you have the material with you, in case you have any question, please let me check if there is one thing we haven't touched today. Any question on that capacitor? I'm waiting, please. I'm waiting. Someone should check.
All right, let's check.
Eh? Hola, I can't hear you.
I said, let's check.
What did she say?
But I'm checking.
Okay. Okay, please check. Okay, I'm waiting. Other person can as well check.
I'm seeing one here, and it has the degree.
Hmm?
The question is long. On page 89.
The question is long. Is it a calculation question? Don't stress yourself already because of exam. Is it don't ask calculation questions. It will just be a waste of time. No long calculation question will come out of exam, actually. Maybe TMS, but exam do not actually bring questions like that. So we observe that in mathematics too. So it doesn't bring so long calculations like that. Should we just continue?
Let's continue.
Mm-hmm. Okay. Resistor in an electric circuit. There is that thing we haven't touched in capacitance. So in capacitance, when capacitors are arranged like this is the symbol for capacitors. Symbol for capacitor. The terminals are the same height. It is different from that of a battery. This is a cell or battery. This is a cell or battery. You can see that the negative terminal is shorter than the positive terminal. The negative terminal is shorter than the positive terminal. But in a capacitor, the positive terminal is the same as the negative terminal. They are of the same height. Did we get the difference between them?
Yes.
Yes.
So these ones now, they are arranged in series. These capacitors are arranged in series like this. So let's say this is the battery, this is the resistor, and this is the key, that's the key there. This is the voltmeter. So like this, they are arranged in series all together like this. This can be C1, C2, C3, and C4. So to know the equivalent capacitor in this circuit now, to know the equivalent capacitor in this circuit, what do? We say the 1 over the equivalent capacitor is equal to 1 over the first capacitor plus 1 over the second capacitor plus 1 over the third capacitor plus 1 over the fourth capacitor. Why are we doing this? Because they are connected in series. For series connection of capacitors, then the reciprocal of the equivalent capacitor is equal to the sum of the reciprocals of the capacitors that made up the circuit. So because they are connected in series. But if they are connected in parallel like this is a capacitor, this is another capacitor, this is another capacitor. You can see they are connected in parallel like this. So we say C1, C2, C3. The total capacitor is going to be C1 plus C2 plus C3. That will be the total capacitor. So this is important to note. We said it that the capacitor is equal to charge over voltage. Don't forget that. So we can use that to find something now. This is an electric circuit. This is 3 microfarad. This is 2 microfarad. This is 1 microfarad. So here now, if a quantity of charge of 5 coulombs, charge is 5 coulombs, is passed through this circuit. The circuit containing all this, what is the electric current in the circuit? What is the electric current in the circuit if the total electric charge passing through it is 5 is? So to know that, we must know the total distance first, the total capacitance. They are connected in parallel, right? So the equivalent capacitance is going to be C equals to C1 plus C2 plus C3. That is 3 plus 2 plus 1. So C is going to be 6 microfarads. That is the total capacitance. And we know that Q is this. So formula, capacitance is equal to Q over V. So to get V now, V is equal to Q over C. So now like this, we can say, what is Q? Q is 5 coulombs. 5 coulombs over C, which is 6 times 10 raised to the power minus 6 farad, because microfarad. So we can do this together now, and we will have 0.83 0.835 and 833 times 10 raised to power 6 voltage. So this will be the potential difference. So doing the normal mathematics around it. So enough of this math. That is capacitance for you. So, and this is the calculation involved in it. They are connected in parallel. The total is this. They are connected in parallel. So they are added this way. So let's see electric, let's see resistors and the lights too. So resistor is capital letter R. What is resistance? Resistance is the opposition offered to the flow of electric current. Resistance is the opposition offered to the flow of electric current. Resistance is the opposition offered to the flow of electric current. So it is represented as capital letter R, and its unit is ohm. We call it ohm, capital letter omega. It is known as ohm, named after the person that stated Ohm's law. So, what does this Ohm's law say? This is a conductor. The conductor has electric current passing through it. Since it has electric current passing through it, so it must be from a battery that is coming. So there is a potential difference across the terminal. So what Ohm's law is telling us is that the higher the potential difference, the higher the electric current. That is, potential difference is directly proportional to the electric current. That is what it's telling us. That is, the potential difference across the terminal of the conductor is directly proportional to the electric current flowing through that conductor. That is it. V directly proportional to I. So this is now written as B equals I R, where R is the constant of proportionality and R is known as the resistor. So if we have resistors arranged like this is the symbol for resistor. If we have resistors arranged like this, R1, R2, R2, then the total resistor is going to be R total is going to be R1 plus R2 plus R3. But if we have them arranged in parallel like this, then R1, R2, R3. Then 1 over R equals to 1 over R1 plus 1 over R2 plus 1 over R3. So the parallel arrangement of resistor, the parallel equation for resistor is going to be the series equation for capacitor. And the series equation of capacitor becomes the parallel equation of resistor. That is what we are trying to say from this. So we have the resistivity, but really becoming very tired. Actually. So that is resistor, and the unit of resistance is ohm. The unit of resistance is ohm. So looking at another thing there, I think that should be the heat here. So when we have resistors heated, so resistor for ohmic resistor, that means resistor that obey Ohm's law. And directly proportional to the temperature. When the temperature increases, it also increases. So there is that thing known as this expansivity, something like expansivity. We are using it here. So we're saying that the coefficient of resistance expansivity or resistivity, expansion coefficient of resistivity is going to be alpha equals to R2 minus R1 all over R1 times theta 2 or T2 minus T1. So this is another important aspect of this resistance of the thing. So I think the other way to help ourselves now, I'm very tired, please. I'm sorry. I'm very, very tired. I'm not well before. I struggle to do. So the other way to help ourselves now is to keep practicing past questions. So I think that's the only next way. Practice past questions. You can't read the material finish. Just read it to the place you think and practice past questions very well. So I wish everyone the best. Please, I'm going to stop there. Sorry. Thank you.